What if I told you that a photon fired from a distant star billions of years ago only decided whether it was a wave or particle the instant you measured it today? That reality itself might be fundamentally uncertain until the moment you choose to observe it. Right now, as you watch this, quantum particles throughout the universe exist in impossible states, being multiple things at once until something forces them to pick just one. Tonight, we're diving into the most mind-shattering revelation in quantum mechanics. The wave function doesn't collapse until you force the universe to choose what actually happened. We'll explore how measurement doesn't just reveal reality, it creates it, and how experiments prove the past remains fluid until the moment you decide to look. Chapter 1. The Quantum Gambling Machine. Imagine reality as the ultimate gambling machine, one that makes Las Vegas look like a children's game. But here's the twist that will blow your mind. This cosmic slot machine never actually pulls the lever. The reels keep spinning forever, showing every possible combination simultaneously, until you walk up and decide to check what you won. Only then, in that precise moment of looking, does the universe finally pick which reality you get to experience. This isn't science fiction. This is the bizarre world revealed by quantum mechanics, where particles exist in what scientists call superposition. Think of it like this. You flip a coin, but instead of landing heads or tails, it somehow manages to be both at the same time. Not just unknown to you, but literally both heads and tails existing together in the same space until you force it to choose. Every electron in your body right now, every photon streaming from your screen, every atom making up the air you breathe, exists in this impossible state of being, multiple things at once. They're spinning clockwise and counterclockwise simultaneously. They're here and there at the same time. They're moving fast and slow, up and down, left and right, all at once. The technical term for this is quantum superposition, but you can think of it as nature's way of keeping all its options open. But here's where it gets really strange. The moment you try to measure one of these particles, the moment you try to pin it down and ask which state it's actually in, something extraordinary happens. All those multiple possibilities suddenly collapse into just one. The spinning electron that was going both ways at once suddenly picks a direction. The particle that was in two places at once suddenly appears in just one spot. It's as if the universe was playing every possible song on its cosmic radio until you tuned in, and only then did it settle on a single station. Scientists call this the collapse of the wave function, and it's one of the most mysterious processes in all of physics. The wave function is like a mathematical recipe that describes all the possible states a quantum particle can be in. Before measurement, this recipe includes every possibility. After measurement, it contains only one actual result. But what triggers this collapse? What forces the universe to stop playing every song at once and pick just one tune? This mystery becomes even more mind-bending when you realize that quantum particles don't just exist in one impossible state at a time. They can be connected to other particles in ways that defy everything we know about space and time. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Change the first particle from spinning both ways to spinning just clockwise, and its partner immediately switches from all possibilities to spinning counterclockwise, even if it's on the other side of the galaxy. Albert Einstein called this spooky action at a distance, and he hated it. He spent years trying to prove that quantum mechanics was incomplete, that there had to be hidden variables determining what particles were really doing behind the scenes. But experiment after experiment has confirmed that Einstein was wrong. The universe really is this strange. Particles really do exist in multiple states at once until measurement forces them to choose. The most famous demonstration of this quantum weirdness is the double-slit experiment. First performed over 2 centuries ago, but still shocking physicists today. Fire a single particle at a wall with 2 slits cut into it. If particles are like tiny balls, each one should go through either the left slit or the right slit, creating 2 strips of hits on a screen behind the wall. But that's not what happens. Instead, the particles create an interference pattern, a series of bright and dark bands that can only form if each individual particle somehow goes through both slits at once and interferes with itself. It's like throwing a single baseball at two doorways and somehow having it pass through both doors simultaneously, creating a pattern that proves it was in two places at the same time. But here's the truly mind-blowing part. The moment you set up detectors to see which slit each particle actually goes through, the interference pattern disappears. Suddenly the particles start behaving like normal objects, going through one slit or the other, never both. The act of measurement, the simple fact that you're trying to observe which path the particle takes, fundamentally changes how the particle behaves. This isn't just a quirk of tiny particles that doesn't affect our everyday world. Remember, everything in our universe is made of quantum particles. Your coffee cup, your smartphone, your own body, all composed entirely of particles that, according to quantum mechanics, should be existing in multiple states at once. So why doesn't your coffee cup exist in a superposition of being on your desk and in your hand simultaneously? Why does our everyday world seem so solid and definite when it's built from components that are fuzzy and uncertain? This question strikes at the heart of one of physics' greatest mysteries, the measurement problem. How does a universe built from quantum uncertainty give rise to the classical certainty we experience every day? When does the quantum world of infinite possibilities transform into the classical world of definite outcomes? And most puzzling of all, what exactly counts as a measurement that can trigger this transformation? Some scientists propose that consciousness itself plays a role in collapsing the wave function. The idea suggests that awareness, the subjective experience of knowing, is what forces quantum possibilities to crystallize into classical reality. Under this view, the universe exists in a state of pure potential until a conscious mind observes it, at which point reality snaps into focus like a photograph developing in a darkroom. Other researchers argue that consciousness has nothing to do with it. They propose that the collapse happens automatically when quantum systems grow large enough or interact with their environment in complex ways. The idea is that the universe has built-in mechanisms that prevent macroscopic objects from existing in superposition states, ensuring that cats are either alive or dead, never both. But perhaps the most radical proposal is that there is no collapse at all. According to the many worlds interpretation, every quantum measurement splits the universe into multiple parallel realities. In one world, the particle goes through the left slit. In another world, it goes through the right slit. Both outcomes happen, just in different versions of reality. You only experience one outcome because you can only exist in one world at a time. But infinite copies of you are experiencing every other possible result in parallel universes. The implications are staggering. If consciousness causes collapse, then minds have a fundamental role in shaping reality itself. If automatic mechanisms prevent quantum weirdness from affecting large objects, then the universe has hidden rules that govern the transition from quantum to classical behavior. If many worlds is correct, then every decision you make, every quantum event in your body, splits reality into countless parallel versions where different choices play out. What makes this mystery even more compelling is that it's not just philosophical speculation. Scientists are actively working to solve the measurement problem through real experiments. They're creating larger and larger quantum systems, pushing the boundaries of where quantum behavior gives way to classical physics. They're testing whether consciousness really does affect quantum systems. They're looking for the physical mechanisms that might cause spontaneous collapse. The answers to these experiments will reshape our understanding of reality itself. They'll tell us whether we live in a single, definite universe or dance across infinite parallel stages. They'll reveal whether consciousness is a fundamental force in physics or simply an emergent property of complex matter. They'll determine whether the universe has hidden mechanisms governing the quantum to classical transition, or whether quantum weirdness extends all the way up to the larger scales. As we dive deeper into this mystery, We'll explore how a simple question about when quantum possibilities become classical realities has grown into one of the most profound puzzles in all of science. We'll see how the act of measurement might not just reveal what's already there, but actually participate in creating the reality we experience. And we'll discover how the universe's strangest property, its ability to exist in multiple states at once, might be the key to understanding everything from consciousness to the nature of time itself. The quantum world doesn't just challenge our intuitions about reality, it forces us to question what reality even means. And as we'll see, the answers emerging from laboratories around the world are stranger than anything science fiction has ever imagined. Chapter 2: The Mathematics of Maybe. The wave function isn't just a mathematical tool that physicists use to make predictions about quantum systems. It is the quantum system. This realization fundamentally changes everything we thought we knew about the nature of reality itself. When we say an electron exists in superposition, we're not saying we don't know which state it's in. We're saying it literally exists in all possible states, simultaneously. And the wave function is the complete mathematical description of this impossible reality. Think of the wave function as reality's instruction manual, written in the language of mathematics. But unlike any instruction manual you've ever seen, this one doesn't tell you how to build one specific thing. Instead, it contains the blueprints for building every possible version of reality at the same time. It's like having architectural plans that simultaneously show a house as a cozy cottage, a towering skyscraper, and everything in between, all existing in the same space until someone decides which version to construct. The mathematical beauty of the wave function lies in its completeness. Give a physicist the wave function of any quantum system, and they can tell you the probability of finding any property at any value when measured. Want to know the chance that an electron will be spinning clockwise? The wave function contains that information. Curious about the likelihood of finding a particle at a specific location? The wave function holds those secrets too. It's like having a cosmic probability calculator that can predict the odds of any possible measurement result. But here's what makes the wave function truly extraordinary. It evolves through time according to one of the most elegant equations in all of physics, the Schrödinger equation. Named after Austrian physicist Erwin Schrödinger, this equation governs how quantum possibilities change and flow through space and time. And unlike the chaotic, unpredictable world we experience in daily life, the evolution of the wave function is completely deterministic. Given the wave function at any moment, the Schrödinger equation can predict exactly what it will look like at any future time. This creates one of the most beautiful paradoxes in science. The wave function, which describes all quantum possibilities, evolves in a perfectly predictable way. Yet when we make measurements on quantum systems, we get random, unpredictable results. It's like having a perfectly choreographed dance that somehow produces improvised music. The underlying mathematical structure is orderly and precise, but the observable outcomes appear completely random. The Schrödinger equation reveals something profound about the nature of quantum mechanics. It's what mathematicians call a linear equation, which means something remarkable about how quantum possibilities combine. If you have two valid solutions to the Schrödinger equation, any combination of those solutions is also a valid solution. This mathematical property is what makes quantum superposition possible. Imagine you have a quantum particle that could be in state A or state B. In classical physics, it would have to be in one state or the other. But quantum mechanics says it can be in both states simultaneously. And the Schrödinger equation treats this combination as just as valid as either individual state. You can have 50% state A plus 50% state B, or 30% A plus 70% B, or any other combination you can imagine. All of these superposition states are perfectly legitimate according to the mathematics. This linearity creates a universe of infinite possibility. A quantum particle isn't limited to being in one of two states, or 10 states, or even a million states. It can exist in a superposition of every possible state simultaneously. An electron can be spinning in every possible direction at once. A photon can be traveling along every possible path through space. A particle can have every possible energy level at the same time. The wave function describes all of these possibilities as equally real and equally present. The Schrödinger equation also has another remarkable property. It's perfectly reversible. Run the equation forward in time, and you can predict how the wave function will evolve into the future. Run it backward, and you can reconstruct exactly what the wave function looked like in the past. This means that no information is ever lost in quantum evolution. Every detail about the quantum state is preserved as the system changes through time. This reversibility stands in stark contrast to our everyday experience of time and change. In the classical world, many processes are irreversible. You can't unbreak an egg, unfry bacon, or turn smoke back into wood. But in the quantum world governed by the Schrödinger equation, every process can theoretically be undone. If you could perfectly reverse all the quantum interactions that scrambled an egg, you could watch it spontaneously reassemble into its original form. Yet despite this mathematical precision and reversibility, quantum mechanics produces measurement results that appear completely random. When you measure a quantum system in superposition, you get one definite outcome, and there's no way to predict which one it will be. You can calculate the probabilities of different results, but the specific outcome of any individual measurement is fundamentally unpredictable. This randomness isn't due to our ignorance or the limitations of our measuring instruments. It's built into the fabric of reality itself. Even if you knew the exact wave function of a quantum system down to the smallest detail, even if you had perfect measuring equipment and unlimited computational power, you still couldn't predict the specific result of a measurement. You could only calculate the odds. The Born rule, named after German physicist Max Born, provides the bridge between the mathematical wave function and experimental probabilities. It states that the probability of measuring any particular value is proportional to the square of the wave function amplitude at that value. If you want to know the chance of finding a particle at a specific location, you look at how large the wave function is at that point, square that value, and you have your probability. This rule has been tested countless times in laboratories around the world, and it has never failed. It allows physicists to make incredibly precise predictions about the statistical behavior of quantum systems. They can tell you exactly what percentage of electrons will be found spinning clockwise, what fraction of photons will pass through a polarizing filter, or how many particles will appear in different regions of space. The Born rule turns the abstract mathematics of the wave function into concrete experimental predictions. But the Born rule also deepens the mystery of quantum mechanics. It tells us how to calculate probabilities from the wave function, but it doesn't explain why measurement produces these random outcomes in the first place. Why does a deterministic wave function evolving according to a predictable equation suddenly produce unpredictable results when we try to observe it? This puzzle becomes even more perplexing when you consider what happens during a measurement. According to the standard interpretation of quantum mechanics, the act of measurement causes the wave function to collapse from a superposition of many possibilities into a single definite state. But this collapse process is completely different from the normal evolution governed by the Schrödinger equation. Normal quantum evolution is linear, reversible, and deterministic. Wave function collapse is nonlinear, irreversible, and random. During normal evolution, information is preserved and all possibilities remain present in the wave function. During collapse, information is lost, and all but one possibility disappear forever. It's as if the universe operates according to two completely different sets of rules. One for when nobody's looking, and another for when someone decides to measure. This dual nature of quantum mechanics creates what physicists call the measurement problem. The theory provides no explanation for when or how the transition from quantum superposition to classical definiteness occurs. There's no equation that describes the collapse process, no principle that determines which possibility becomes reality, and no clear definition of what constitutes a measurement in the first place. The measurement problem reveals a fundamental gap in our understanding of quantum mechanics. We have a beautiful mathematical framework that makes incredibly accurate predictions about the statistical behavior of quantum systems. But we have no coherent physical picture of what's actually happening when quantum possibilities become classical realities. Some physicists argue that this gap doesn't matter. They point out that quantum mechanics works perfectly well for all practical purposes. You can use it to design computer chips, build lasers, create medical imaging devices, and develop quantum technologies without ever solving the measurement problem. From this pragmatic perspective, asking what really happens during measurement is like asking what color Wednesday is. An interesting philosophical question, but not one that affects the usefulness of the theory. But other scientists find this attitude unsatisfying. They argue that a complete theory of physics should provide a coherent picture of physical reality, not just a recipe for calculating experimental results. If quantum mechanics is truly fundamental, then it should explain how the classical world we experience emerges from quantum foundations. The measurement problem isn't just a technical puzzle, it's a sign that our understanding of reality itself is incomplete. The mathematical structure of quantum mechanics also raises deep questions about the nature of physical properties. In classical physics, objects have definite properties whether we observe them or not. A spinning top has a specific rotation rate, a moving car has a particular velocity, and a colored object reflects certain wavelengths of light, all independent of any measurements we might make. But quantum mechanics suggests that particles don't have definite properties until they're measured. The wave function doesn't describe our knowledge of particle properties. It describes the particle itself. Before measurement, an electron doesn't have a definite spin direction hidden somewhere that we just happen not to know. Instead, it literally exists in a superposition of all possible spin directions simultaneously. This idea challenges our most basic intuitions about reality. We're used to thinking that measurement reveals pre-existing properties, like opening a box to see what color marble is inside. But quantum mechanics suggests that measurement actually creates properties, like reaching into an empty box and somehow causing a marble of a specific color to spontaneously appear. The implications extend far beyond individual particles. If quantum mechanics is correct, then complex systems made of many particles should also exist in superposition states until measured. A molecule should exist in multiple shapes at once. A chemical reaction should follow all possible pathways simultaneously. Even large objects should, in principle, be able to exist in quantum superposition. Yet we never observe macroscopic superposition in everyday life. Cats are never both alive and dead. Coffee cups never exist in two places at once. Cars never drive multiple routes simultaneously. Something prevents quantum weirdness from affecting the world we can see and touch directly. This quantum to classical transition is one of the deepest mysteries in physics. How does a universe built from quantum building blocks give rise to classical behavior? Where and when does the transition occur? What determines which quantum possibilities become classical realities? The mathematical formalism of quantum mechanics provides no answers to these questions. The Schrödinger equation works equally well for single particles and complex systems. The Born rule applies to measurements on large objects just as much as small ones. Nothing in the basic theory explains why quantum behavior seems to disappear at macroscopic scales. Some scientists propose that the quantum to classical transition occurs through interaction with the environment. They argue that large systems can't maintain quantum coherence because they're constantly being disturbed by external influences. Every collision with an air molecule, every absorption of a photon, every tiny interaction with the surroundings gradually destroys the delicate quantum relationships that enable superposition. This process, called decoherence, might explain why macroscopic objects appear classical, even though they're made of quantum particles. The environment acts like a constant stream of tiny measurements, gradually collapsing macroscopic wave functions into definite states. From this perspective, the classical world emerges not because of any fundamental change in physics, but because large systems can't stay isolated from their surroundings long enough to maintain quantum coherence. But decoherence alone doesn't solve the measurement problem. It explains why quantum effects become unobservable in large, complex systems, but it doesn't explain why individual measurement outcomes are definite rather than remaining in superposition. Even with decoherence, the mathematics of quantum mechanics still predicts that measurement devices should exist in superposition states, corresponding to all possible measurement results. The measurement problem forces us to confront fundamental questions about the nature of reality itself. Is the wave function a complete description of physical systems? Or does it only capture our knowledge about systems whose true properties remain hidden? Does the collapse of the wave function represent a real physical process? Or is it just a useful mathematical trick for calculating measurement probabilities? These questions have puzzled physicists for nearly a century, and they remain hotly debated today. Different answers lead to radically different pictures of reality, from conscious observers creating the universe through measurement to infinite parallel worlds where every quantum possibility actually occurs. As we explore deeper into the mystery of quantum measurement, we'll see how this mathematical puzzle about wave functions and probabilities connects to some of the most profound questions human beings have ever asked about consciousness, reality, and our place in the cosmic order. The mathematics of quantum mechanics doesn't just describe the behavior of particles. It challenges our most fundamental assumptions about what it means for something to be real. Chapter 3: When Consciousness Meets Cosmos. The most radical and controversial proposal in all of quantum mechanics emerged from a simple but shocking question. What if consciousness itself is the force that collapses the wave function? What if the universe exists in a hazy soup of infinite possibilities until a conscious mind observes it, at which point reality crystallizes into the single world we experience? This idea doesn't just challenge our understanding of physics, it suggests that minds play a fundamental role in creating the very fabric of reality itself. The consciousness interpretation of quantum mechanics began with some of the most brilliant scientists of the 20th century. John von Neumann, the mathematical genius who helped develop both quantum theory and the modern computer, was the first to seriously propose that consciousness might be the missing ingredient in quantum measurement. In the 1930s, von Neumann analyzed the mathematics of quantum mechanics and reached a startling conclusion. According to the equations, measurement devices should also exist in quantum superposition, along with the systems they measure. Think about what this means. When you use a detector to measure whether an electron is spinning clockwise or counterclockwise, quantum mechanics predicts that the detector itself should end up in a superposition state. It should simultaneously show readings of both clockwise and counterclockwise until something collapses its wave function too. But then you need another device to measure the first detector, and that device will also be in superposition. You end up with an infinite chain of measuring devices, all stuck in superposition states, with no way to get a definite answer about anything. Von Neumann realized that somewhere in this chain, the buck has to stop. Something has to cause the collapse that gives us definite measurement results instead of eternal superposition. He proposed that this something is consciousness itself. When a conscious observer becomes aware of a measurement result, their subjective experience causes the entire chain of quantum superposition to collapse into a single, definite outcome. This idea was further developed by Eugene Wigner, von Neumann's colleague and fellow Nobel Prize winner. Wigner argued that consciousness is fundamentally different from all other physical processes because it produces definite, subjective experiences rather than quantum superpositions. When you see a red apple, you experience definite redness, not a superposition of all possible colors. When you feel happy or sad, you experience definite emotions, not probability clouds of all possible feelings. Wigner proposed that this definiteness of conscious experience is what breaks the quantum chain. Consciousness, he argued, is the only thing in the universe that naturally exists in definite states rather than superposition. Therefore, it's the only thing capable of collapsing quantum wave functions and creating the classical reality we observe. The implications of the consciousness interpretation are staggering. If minds cause wave function collapse, then consciousness isn't just an accidental byproduct of complex matter. It's a fundamental force in physics, as important as gravity or electromagnetism. Without conscious observers, the universe would remain forever locked in a state of pure quantum potential, never actualizing any specific reality. Under this view, the evolution of consciousness becomes a cosmic necessity rather than a biological accident. The universe needs minds to observe it in order to become real. The emergence of conscious life isn't just interesting from a biological perspective. It's the moment when the cosmos gains the ability to transform quantum possibilities into classical actualities. This interpretation also suggests that consciousness has genuine causal power over physical events. Your decision to observe a quantum system doesn't just reveal a pre-existing reality. It actually participates in creating that reality by forcing the universe to choose one possibility from among infinite alternatives. Every conscious observation becomes an act of cosmic creation, collapsing probability clouds into definite facts. But the consciousness interpretation faces serious challenges that have made most physicists skeptical of its claims. The first problem is defining exactly what counts as consciousness. If human awareness causes wave function collapse, what about animal consciousness? Do dogs and cats collapse wave functions when they observe quantum systems? What about insects? Or bacteria? Or plants? Where do you draw the line between conscious and unconscious systems? The problem becomes even more challenging when you consider that consciousness seems to come in degrees rather than being an all-or-nothing property. A fully alert adult human certainly seems conscious, but what about someone who's drowsy or dreaming or under anesthesia? Do these different states of consciousness have different effects on quantum collapse? Can a half-conscious person only partially collapse a wave function? There's also the question of when consciousness first appeared in the universe's history. If consciousness is required for wave function collapse, then quantum systems couldn't have definite properties before conscious beings evolved. The early universe would have existed in pure superposition for billions of years, until the first primitive minds appeared. Stars, planets, and galaxies would have remained quantum phantoms until consciousness emerged to observe them into existence. This leads to a paradoxical chicken and egg problem. Consciousness presumably evolved through natural selection operating on biological systems with definite properties. But if consciousness is required to collapse wave functions and create definite properties, how could evolution occur before consciousness existed? How can you have natural selection among organisms that exist only in quantum superposition? Another major challenge is the apparent randomness of quantum measurement results. If consciousness causes collapse, you might expect that conscious will or intention could influence which outcome occurs. After all, if minds have the power to collapse wave functions, perhaps they also have some control over how the collapse happens. But experiments show no evidence that conscious intention affects quantum measurement results. The outcomes remain stubbornly random, regardless of what the observer hopes or expects to see. The consciousness interpretation also struggles with the practical reality of how quantum experiments actually work. In modern physics laboratories, most quantum measurements are performed by automated equipment with no human observers present. Computers record the data, analyze the results, and store the information for later review. If consciousness is required for collapse, when exactly does it occur in these automated experiments? Does the collapse wait until a human scientist eventually looks at the computer data, potentially hours or days later? These practical concerns have led most physicists to reject the consciousness interpretation in favor of alternatives that don't require minds to play special roles in physics. But the idea hasn't disappeared entirely. It continues to attract interest from researchers exploring the connections between physics and consciousness, as well as from philosophers grappling with the hard problem of conscious experience. Some modern versions of the consciousness interpretation try to address these challenges by proposing more sophisticated mechanisms for how minds might interact with quantum systems. Rather than requiring human-level consciousness for collapse, these theories suggest that even simple information processing systems might be able to collapse wave functions. Any system that can record and store information about quantum states might trigger collapse, whether it's a conscious brain, a computer memory, or even a simple molecular recording mechanism. This approach potentially solves the problem of defining consciousness by removing the requirement for subjective awareness altogether. Instead of consciousness per se, these theories focus on the emergence of classical information from quantum superposition. Any physical process that creates stable, definite records of quantum events could trigger collapse, regardless of whether conscious minds are involved. But this modification raises new questions about what makes information processing special in physics. Why should the ability to record information break quantum superposition when other physical interactions don't? What distinguishes information storage from any other form of physical correlation? If any information recording process can cause collapse, then nearly every interaction in the universe becomes a potential collapse trigger. Which brings us back to the question of why quantum effects seem to persist at all. The consciousness interpretation also intersects with deep philosophical questions about the nature of mind and matter. If consciousness can influence physical systems through quantum collapse, then mental states have real causal power over material events. This challenges the materialist view that everything in the universe, including consciousness, can be reduced to the behavior of particles following physical laws. Instead, consciousness becomes something genuinely new and different, possessing causal powers that can't be explained purely in terms of material interactions. This doesn't necessarily require supernatural explanations, but it does suggest that consciousness involves physical principles we don't yet understand. Perhaps there are aspects of physics beyond our current theories that become relevant only when matter organizes itself into conscious systems. The quantum consciousness connection has also inspired speculation about whether quantum effects might be relevant to understanding how consciousness actually works. Some researchers have proposed that the brain might exploit quantum coherence to perform computations that would be impossible using purely classical processors. Quantum superposition might allow neural networks to explore multiple solutions to problems simultaneously, while quantum entanglement might enable different parts of the brain to coordinate their activities in novel ways. These ideas remain highly speculative and controversial. The brain seems like an unlikely place for quantum effects to survive, given its warm, wet, noisy environment. Quantum coherence typically requires extremely cold temperatures and careful isolation from environmental disturbances. The biological conditions inside neural tissue seem perfectly designed to destroy quantum coherence as quickly as possible. However, recent discoveries have shown that biological systems can sometimes exploit quantum effects even in warm, complex environments. Photosynthesis in plants involves quantum coherence that persists for surprisingly long times despite thermal noise. Some bird species appear to use quantum entanglement in their navigation systems. These findings suggest that evolution has found ways to harness quantum mechanics for biological functions, even under conditions that seemed prohibitive. Whether similar quantum effects occur in consciousness remains an open question. Even if they do, it's unclear whether such effects would be relevant to the measurement problem in quantum mechanics. The quantum processes involved in consciousness might be completely separate from those involved in wave function collapse. Having quantum effects in your brain doesn't necessarily mean your consciousness can collapse quantum systems outside your body. The consciousness interpretation forces us to confront fundamental questions about the relationship between mind and matter that go far beyond physics. If consciousness plays a role in determining physical reality, then understanding the nature of conscious experience becomes crucial for understanding the universe itself. The hard problem of consciousness, how subjective experience arises from objective matter, becomes intertwined with the measurement problem in quantum mechanics. These connections suggest that resolving the quantum measurement problem might require insights from neuroscience, psychology, and philosophy of mind, not just physics. Understanding how consciousness works might be the key to understanding how quantum possibilities become classical realities. Alternatively, solving the measurement problem might shed light on the nature of consciousness itself. The consciousness interpretation also raises profound questions about the role of observers in science. Traditional scientific methodology assumes that observers can study reality without fundamentally affecting it. Measurements reveal pre-existing properties rather than creating new ones. But if consciousness causes wavefunction collapse, then the act of scientific observation becomes an act of reality creation. Scientists don't just discover what's there, they participate in bringing reality into existence through their conscious observations. This doesn't necessarily undermine the objectivity of science, but it does suggest that the relationship between observers and reality is more complex than traditionally assumed. The properties we measure might depend not just on the systems we study, but also on the conscious minds doing the studying. This could lead to a more participatory view of science, where human consciousness becomes an acknowledged part of the experimental process, rather than something to be eliminated or controlled. Despite decades of debate and research, the consciousness interpretation of quantum mechanics remains unresolved. No experiment has definitively proven or disproven the role of consciousness in wavefunction collapse. The interpretation continues to evolve as our understanding of both quantum mechanics and consciousness advances. What's certain is that the consciousness interpretation has forced physicists to grapple with questions they might otherwise have ignored. It has highlighted the deep connections between the measurement problem in quantum mechanics and the hard problem of consciousness. It has challenged the assumption that physics can be completely separated from questions about mind and experience, whether or not consciousness actually causes wave function collapse. The idea has enriched our understanding of both quantum mechanics and the nature of conscious experience. It reminds us that the deepest mysteries in science often occur at the intersections between different fields of knowledge, where physics meets psychology, where matter encounters mind, and where the objective world of science engages with the subjective reality of human experience. As we continue exploring the quantum measurement problem, we'll see how other interpretations try to solve the puzzle without invoking consciousness, and how new experiments might finally determine whether minds play special roles in the fundamental workings of reality. The conversation between consciousness and cosmos continues, pushing us toward ever deeper understanding of what it means to be conscious observers in a quantum universe. Chapter 4: The Objective Reality Revolution. In 1986, 3 Italian physicists made a proposal so radical that it would completely revolutionize how we think about the quantum measurement problem. Giancarlo Girardi, Alberto Rimini, and Tullio Weber suggested something that sounded almost heretical to the physics community. What if wave function collapse isn't caused by conscious observers or mysterious measurement processes? What if it happens spontaneously, randomly, and automatically as a fundamental feature of how the universe works? Their theory, known as GRW after their initials, launched an entirely new approach to understanding quantum mechanics, called objective collapse theories. The central insight of objective collapse theories is breathtakingly simple, yet profound. Instead of requiring special explanations for why wave functions collapse during measurements, these theories propose that collapse happens all the time, everywhere in the universe, as a basic physical process. Quantum systems don't need conscious observers or complex measuring devices to transition from superposition to definite states. They do it spontaneously, driven by the same kind of fundamental randomness that governs radioactive decay or quantum tunneling. Think of it like this. Imagine every quantum particle in the universe as a cosmic coin that's constantly flipping itself. Most of the time, these quantum coins stay suspended in midair, showing both heads and tails simultaneously. But occasionally, completely at random, a coin decides to land. When it does, it forces every other coin connected to it to land as well. creating a cascade of definite outcomes from what was previously pure possibility. This spontaneous collapse mechanism solves the measurement problem in an elegant way. You don't need to define what counts as a measurement because there's no special role for measurements at all. Quantum systems collapse into definite states on their own schedule, following statistical rules that have nothing to do with observers or measuring devices. The classical world emerges naturally from quantum foundations, without requiring consciousness, complex interactions, or mysterious boundary conditions. The GRW theory makes this idea mathematically precise by modifying the Schrödinger equation. Remember, the standard Schrödinger equation describes smooth, continuous evolution of quantum systems in perfect superposition states. But Gerardi, Rimini, and Weber added new terms to this equation that represent spontaneous collapse events. These additional terms cause wave functions to suddenly and randomly localize at specific positions in space. The collapse process in GRW theory works like a series of random hits that quantum systems take from some unknown source. Picture each particle as being pelted by invisible quantum bullets that strike completely at random. Most of the time, these bullets miss, and the particle continues evolving in superposition, according to the normal Schrödinger equation. But occasionally, a bullet hits its target, causing the particle's wave function to instantly collapse to a definite position. The beauty of this mechanism lies in how rarely these hits occur for individual particles. Gerardi, Rimini, and Weber calculated that a single isolated quantum particle should experience spontaneous collapse only about once every 100 million years. This incredibly low rate ensures that individual particles and small quantum systems can maintain superposition states for as long as necessary to exhibit all the strange quantum behaviors we observe in laboratory experiments. But here's where the theory becomes truly clever. Although individual particles rarely experience collapse, the probability of collapse increases dramatically when many particles become entangled together. If you have two entangled particles, the chance that one of them will experience a collapse event doubles. With 1,000 entangled particles, the collapse rate increases 1,000-fold. When you reach the enormous numbers of particles in everyday objects, collapse becomes virtually inevitable. Consider an ordinary grain of sand, which contains approximately 10 to the 19th power atoms. According to GRW theory, with this many particles all quantum mechanically connected, collapse events should occur roughly every 10 nanoseconds. That means the grain of sand can never maintain quantum superposition for more than a few billionths of a second before spontaneous collapse forces it into a definite classical state. This size-dependent collapse rate provides a natural explanation for why quantum effects seem to disappear at macroscopic scales. Small systems with few particles can stay quantum for long periods because collapse events are rare. Large systems with many particles automatically become classical because collapse events happen constantly. The quantum to classical transition isn't caused by measurement or environmental interference. It's a direct consequence of how many particles are involved in the quantum system. The GRW mechanism also explains why measurements produce definite results without requiring special physical processes or conscious observers. When you use a measuring device to observe a quantum system, you're necessarily bringing huge numbers of particles into contact with the quantum state you want to measure. The device might contain trillions of atoms in its electronics, crystals, or mechanical components. With this many particles becoming entangled with the quantum system being measured, spontaneous collapse becomes unavoidable within fractions of a second. From this perspective, measuring devices don't cause collapse through any special property they possess as measurement apparatus. They cause collapse simply because they're large, complex objects containing enormous numbers of particles. A sophisticated quantum detector and a random chunk of matter would have similar effects on quantum superposition, both triggering collapse through the sheer number of particles involved rather than through any designed measurement function. This insight led to the development of more sophisticated objective collapse theories that refine the GRW approach. The most prominent of these is continuous spontaneous localization, known as CSL, developed by Philip Pearl and Giancarlo Girardi in the early 1990s. Instead of discrete, violent collapse events hitting particles at random intervals, CSL describes collapse as a continuous process driven by fluctuating fields that permeate all of space. Imagine the entire universe filled with an invisible, randomly jittering field, like the quantum equivalent of ocean waves constantly washing over everything. This field interacts with matter in a way that gradually collapses quantum superpositions, with the strength of the interaction depending on how much matter is present. Individual particles barely feel these fluctuations and can maintain superposition for long periods. But large collections of matter experience strong interactions with the field, causing their wave functions to collapse quickly and continuously. The CSL model addresses some technical problems with the original GRW theory, while preserving its basic insight that collapse happens spontaneously without requiring observers or measurements. The continuous nature of the collapse process eliminates the sudden, instantaneous changes that made some physicists uncomfortable with discrete collapse events. Instead, quantum superpositions gradually fade away as the fluctuating field steadily pushes quantum systems toward classical definiteness. Both GRW and CSL theories face a fundamental challenge in explaining what actually causes the spontaneous collapse events. The theories describe the mathematical structure of how collapse occurs and predict when it should happen, but they don't identify the physical mechanism responsible for triggering these events. It's as if we have precise equations describing how invisible quantum bullets affect matter without knowing what shoots the bullets or where they come from. This gap in understanding led to the development of a third major objective collapse theory that attempts to identify a specific physical cause for spontaneous collapse. The Diossi-Penrose model, developed independently by Lajos Diossi and Roger Penrose in the late 1980s and early 1990s, proposes that gravity itself is responsible for collapsing quantum wave functions. The gravitational collapse idea is based on a profound insight about the relationship between quantum mechanics and general relativity. When a quantum system exists in spatial superposition, different components of its wave function are located at different positions in space. According to Einstein's theory of general relativity, mass and energy curve spacetime, which means each component of the superposed wave function creates its own slightly different gravitational field. Penrose argued that this situation creates an unstable conflict between quantum mechanics and general relativity. Quantum theory says the system should remain in superposition indefinitely, with each component following its own path through spacetime. But general relativity suggests that having multiple, incompatible gravitational fields in the same region of space should be energetically costly and unstable. The Diossi-Penrose model resolves this conflict by proposing that gravitational effects automatically collapse quantum superpositions when the energy difference between different gravitational configurations becomes too large. The universe, in effect, cannot tolerate having multiple contradictory gravitational fields in the same place for extended periods. When the gravitational energy differences reach a critical threshold, the system spontaneously collapses to a single definite configuration. This gravitational mechanism provides a natural explanation for why larger, more massive objects experience faster collapse rates. More massive systems create stronger gravitational fields, leading to larger energy differences between superposed states and faster collapse times. The theory predicts that collapse rates should be proportional to the square of the mass involved, which matches the general pattern observed in proposed objective collapse models. The gravitational approach also suggests fascinating connections between quantum mechanics and cosmology. If gravity drives quantum collapse, then the structure of spacetime itself plays a role in determining how quantum possibilities become classical realities. The expansion of the universe, the presence of massive objects like stars and black holes, and the overall geometry of spacetime could all influence how quickly quantum systems collapse. One of the most appealing features of objective collapse theories is that they make testable predictions that differ from standard quantum mechanics. Unlike interpretational approaches that make identical predictions but offer different philosophical perspectives. Objective collapse models predict specific physical effects that could be detected experimentally. The most promising experimental signature involves the energy released during spontaneous collapse events. When a quantum system collapses from a spread-out superposition state to a localized definite state, the theory predicts that small amounts of energy should be released as radiation. This collapse radiation should have specific characteristics that depend on the details of the collapse mechanism. For example, the CSL model predicts that spontaneous localization should produce a continuous spectrum of electromagnetic radiation with intensities that depend on the strength of the collapse field and the amount of matter involved. This radiation should be detectable using sensitive instruments, provided the collapse parameters are within the range suggested by theoretical considerations. The challenge lies in detecting extremely weak signals against the background of other radiation sources. The predicted collapse radiation is incredibly faint, requiring experiments with exceptional sensitivity and careful shielding from environmental noise. Several research groups around the world have attempted these measurements using underground laboratories, superconducting detectors, and other advanced techniques. The most sophisticated experiments have been conducted at the Gran Sasso National Laboratory in Italy, deep underground to minimize cosmic ray interference. Researchers have used germanium crystals cooled to extremely low temperatures, monitoring them for months at a time to detect the faint photons that collapse. Theories predict should be continuously emitted from all matter. These experiments have placed increasingly stringent limits on the parameters of various collapse models. Some versions of the theories have been ruled out entirely, while others remain consistent with experimental bounds but require very specific parameter values. The ongoing experimental program represents one of the most direct attempts to test fundamental modifications to quantum mechanics. Beyond radiation detection, objective collapse theories suggest other experimental tests involving the behavior of quantum systems as they grow in size and complexity. The theories predict specific thresholds where quantum coherence should break down due to spontaneous collapse, independent of environmental decoherence effects. Experiments with levitated nanoparticles, biological molecules, and other mesoscopic systems are beginning to probe these predicted boundaries. The theoretical development of objective collapse models has also revealed deep connections to other areas of physics. The stochastic processes that drive spontaneous collapse are mathematically similar to those found in statistical mechanics, condensed matter physics, and quantum field theory. These connections suggest that collapse phenomena might be related to other fundamental aspects of physics beyond the measurement problem. Some researchers have explored whether objective collapse effects might be relevant to understanding other puzzles in physics, such as the arrow of time, the second law of thermodynamics, or the emergence of classical spacetime from quantum gravity. If collapse represents a fundamental irreversible process in nature, it might play broader roles in explaining why the universe exhibits temporal asymmetry and thermodynamic behavior. The objective collapse approach also provides a framework for thinking about quantum mechanics in cosmological contexts. If collapse happens spontaneously throughout the universe, then even regions of space with no observers or measuring devices should experience continuous transitions from quantum possibility to classical actuality. This suggests that the entire cosmic wave function is constantly collapsing and reforming, creating a dynamic picture of reality that's constantly crystallizing from quantum potential. These cosmological implications raise fascinating questions about the early universe and the origin of classical structures like galaxies, stars, and planets. If objective collapse was operating during the first moments after the Big Bang, it might have played a role in breaking the initial quantum symmetries and creating the classical inhomogeneities that eventually grew into the large-scale structure we observe today. The objective collapse revolution represents more than just a new approach to the measurement problem. It suggests that the transition from quantum to classical behavior might be governed by fundamental physical principles that we're only beginning to understand. Rather than being an artifact of observation or measurement, the emergence of classical reality might be woven into the basic fabric of space-time itself. As experimental techniques continue to improve and theoretical understanding deepens, objective collapse theories offer the tantalizing possibility of finally resolving one of the deepest mysteries in physics. They promise a universe where quantum possibilities naturally evolve into classical realities through spontaneous objective processes that require no special role for consciousness, measurement, or environmental interaction. The revolution begun by Girardi, Rimini, and Weber continues to unfold, pushing us toward a new understanding of how the strange quantum world gives birth to the familiar classical reality we experience every day. Whether spontaneous collapse, gravitational effects, or some other objective mechanism drives this transition, the search for answers is revealing profound truths about the fundamental nature of reality itself. Chapter 5: The future rewrites the past. Imagine firing a photon from Earth toward a distant galaxy. Then billions of years later, long after that photon has completed its journey, deciding whether to look for wave-like interference patterns or particle-like behavior in its detection. Common sense tells us this should be impossible. The photon's journey happened in the ancient past. Its behavior during that voyage should be a fixed historical fact, unchangeable by any decision we make today. Yet, quantum mechanics suggests something far stranger. The photon's past behavior might remain undetermined until the moment we choose how to observe it. This mind-bending possibility lies at the heart of John Wheeler's delayed choice experiments. Thought experiments so profound they challenge our most basic assumptions about time, causality, and the nature of reality itself. Wheeler, one of the most visionary physicists of the 20th century, proposed that quantum systems might not just be uncertain about their future states, but could also remain undecided about their past behavior until forced to choose by present moment observations. The delayed choice concept emerged from Wheeler's deep thinking about the famous double-slit experiment and its implications for the nature of light. In the standard version of this experiment, photons or electrons create interference patterns when fired at a screen with two slits, but only when no information is available about which slit each particle passes through. The moment you set up detectors to monitor the particle paths, the interference pattern disappears and the particles behave like classical objects going through one slit or the other. This wave-particle duality has puzzled physicists since the early days of quantum mechanics. But Wheeler realized that most discussions of the double-slit experiment contained a hidden assumption that might not be valid. Scientists typically assume that particles somehow decide whether to behave like waves or particles when they encounter the double-slit apparatus. The choice between wave and particle behavior seemed to happen at the beginning of the experiment, when the quantum system first interacts with the experimental setup. Wheeler asked a more radical question. What if this assumption is wrong? What if quantum systems don't make any commitments about their behavior until the very end of an experiment, when they're finally detected and measured? What if the decision between wave and particle behavior can be delayed until long after the quantum system has supposedly made its choice? To test this idea, Wheeler devised a thought experiment that pushes the delayed choice concept to cosmic extremes. Imagine light from a distant quasar, one of the most luminous objects in the universe, traveling for billions of years across space before reaching Earth. Along the way, this light encounters a massive galaxy whose gravitational field acts like a cosmic lens, bending the light, rays, and creating two possible paths that the photons could follow to reach our telescopes. From our perspective on Earth, the quasar appears as two separate images in the sky, even though the light comes from a single source. This gravitational lensing effect gives us the cosmic equivalent of a double-slit experiment, with the galaxy playing the role of the barrier with two openings. The light from the quasar can reach Earth by following either the path around one side of the galaxy or the path around the other side. Now comes Wheeler's crucial insight. We can choose to observe this cosmic light in two fundamentally different ways, and we can make this choice billions of years after the photons began their journey. We could set up our telescopes to detect the two separate images of the quasar, which would give us information about which path each photon followed around the gravitational lens. This would reveal the particle-like nature of the light. Alternatively, we could combine the light from both images using sophisticated interferometry techniques, looking for interference patterns that would demonstrate the wave-like nature of the photons. If the light behaved as waves during its cosmic journey, combining the two paths should produce measurable interference effects. The shocking implication is that our choice of measurement strategy made today might determine how the photons behave during their billions-year journey through space. If we choose to measure particle properties, the photons would have traveled as particles, following definite paths around one side of the galaxy or the other. If we choose to measure wave properties, the same photons would have traveled as waves, somehow taking both paths simultaneously and interfering with themselves across galactic distances. This seems to violate everything we know about causality and the flow of time. How can a decision made in the present affect events that happened in the distant past? How can the behavior of light during its cosmic journey depend on choices we haven't even made yet when that journey began? Wheeler's delayed choice experiment forces us to confront the possibility that the past might not be as fixed and determined as we assume. In quantum mechanics, the future is probabilistic and uncertain until observations collapse, wave functions into definite outcomes. Wheeler suggested that the past might be equally uncertain, remaining in a quantum superposition of different possible histories until present moment observations force it to crystallize into a single, definite narrative. The delayed choice concept becomes even more mysterious when applied to quantum entanglement, leading to what physicists call the delayed choice quantum eraser. This variation of Wheeler's idea uses pairs of entangled photons to create situations where decisions about one photon seem to retroactively determine the behavior of its partner, even after that partner has already been detected and recorded. The quantum eraser experiment begins with a source that produces pairs of entangled photons, quantum particles that remain mysteriously connected regardless of how far apart they travel. One photon from each pair, called the signal photon, passes through a double-slit apparatus and hits a detection screen. The other photon, called the idler photon, follows a different path toward a separate detector system. The key insight is that the idler photon carries information about which slit its entangled partner passed through. By measuring the idler photon in different ways, experimenters can either preserve or erase this which path information. When the which path information is preserved, the signal photons on the screen show no interference pattern, behaving like particles. When the which path information is erased, the signal photons display clear interference fringes, demonstrating wave-like behavior. The delayed choice quantum eraser pushes this setup to its logical extreme by making the decision to preserve or erase the which path information long after the signal photons have already hit the detection screen. The idler photons can be sent on extended journeys, traveling for minutes, hours, or even days before reaching their detector. Only then do experimenters decide whether to measure the idler photons in a way that preserves or erases the which path information. The results seem to defy common sense and our understanding of time. Even though the signal photons have already been detected and their positions permanently recorded, the pattern they form on the screen depends on future decisions about how to measure their entangled partners. If experimenters later choose to preserve which path information, the signal photons will have formed a particle-like pattern with no interference. If they choose to erase which path information, the same signal photons will have formed a wave-like interference pattern. This apparent retrocausal influence has led some interpreters of quantum mechanics to suggest that information can travel backward in time, allowing future events to influence past occurrences. Under this view, Quantum mechanics reveals that the universe has a fundamentally different temporal structure than we experience in everyday life. The past, present, and future might be more interconnected than classical physics suggests, with quantum correlations creating bridges across time that allow later decisions to affect earlier events. However, most physicists reject retrocausal explanations of delayed choice experiments, arguing that they can be understood without invoking backward time travel or violations of causality. The key insight is that quantum entanglement creates correlations between distant events without requiring any form of communication or influence between the entangled systems. When two photons are entangled, they don't have separate, independent properties that somehow influence each other across space and time. Instead, they form a single quantum system described by a combined wavefunction that encompasses both particles simultaneously. The correlations revealed by delayed choice experiments don't represent one photon affecting its partner. They represent the manifestation of pre-existing quantum relationships that were established when the entanglement was first created. From this perspective, delayed choice experiments don't show that the future affects the past. They reveal that quantum systems can remain in superposition states much longer than we typically assume. The signal photons don't form definite interference patterns until the complete experimental context is established, including whatever happens to their entangled partners. The apparently retroactive effects are actually manifestations of quantum superposition, persisting until all relevant measurements are completed. This interpretation preserves our normal understanding of causality while still acknowledging the strange quantum correlations revealed by delayed choice experiments. No information travels faster than light or backward in time. Instead, quantum systems demonstrate a kind of holistic behavior where the properties of individual components depend on the total configuration of the entire system, even when that system spans vast distances or extends across significant time intervals. The delayed choice quantum eraser has been implemented in numerous laboratory experiments, confirming the theoretical predictions and ruling out various classical explanations for the observed correlations. These experiments use sophisticated optical setups with beam splitters, mirrors, and detectors arranged to create the necessary entanglement relationships and measurement choices. One of the most striking implementations involves sending idler photons through optical fibers that can be kilometers long, creating genuine time delays between the detection of signal photons and the measurement choices that determine their apparent behavior. These experiments confirm that the correlations persist even when the time delays are large enough to eliminate any possibility of light-speed communication between the measurement events. The results consistently support the quantum mechanical predictions while ruling out models based on hidden variables or classical correlations. The delayed choice effects appear to be genuine quantum phenomena that cannot be explained using conventional ideas about how information and influence propagate through space and time. Recent experiments have pushed delayed choice concepts even further, implementing versions with quantum systems other than photons and exploring scenarios with multiple levels of delayed choice. Researchers have demonstrated delayed choice effects with atoms using matter wave interferometry to show that massive particles exhibit the same mysterious temporal correlations as photons. Other experiments have explored hierarchical delayed choice scenarios where the decision about whether to implement a delayed choice is itself delayed until after the initial quantum events have occurred. These nested experiments create even more complex temporal relationships, suggesting that quantum superposition can encompass not just the physical states of particles, but also the measurement strategies used to observe them. The implications of delayed choice experiments extend far beyond the technical details of quantum mechanics. They challenge our fundamental assumptions about the nature of time, causality, and physical reality. If quantum systems can remain undetermined about their past behavior until future observations force them to choose, then the boundary between past, present, and future becomes much more fluid than classical physics suggests. These experiments also raise profound questions about the role of information in physics. The delayed choice quantum eraser shows that whether a quantum system exhibits wave or particle behavior depends not on local interactions with measurement apparatus, but on the global information available about the complete experimental setup. This suggests that information, rather than matter and energy, might be the most fundamental aspect of physical reality. The delayed choice concept has inspired speculation about whether similar quantum effects might operate in other contexts beyond controlled laboratory experiments. Some researchers have proposed that quantum superposition and delayed collapse might play roles in biological systems, consciousness, or cosmological evolution. While these ideas remain highly speculative, they illustrate how delayed choice experiments continue to push the boundaries of our understanding. The ongoing development of quantum technologies has also opened new possibilities for implementing delayed choice experiments with unprecedented precision and control. Quantum computers and quantum communication networks might enable delayed choice scenarios that are impossible with current technology, potentially revealing new aspects of quantum temporal correlations. As we continue to probe the implications of Wheeler's delayed choice concept, we're discovering that time itself might be far stranger than we ever imagined. The classical picture of a fixed past, dynamic present, and uncertain future may be too simplistic to capture the full reality of quantum existence. Instead, we might inhabit a universe where past, present, and future form an intricate quantum web of possibilities that crystallize into definite realities only when the complete story of observation and measurement unfolds. The delayed choice experiments remind us that quantum mechanics isn't just a theory about small particles behaving strangely in laboratories. It's a fundamental description of how reality itself operates, with implications that reach from the microscopic quantum realm to the cosmic scales where light from distant quasars carries messages about the deepest nature of space, time, and existence itself. Chapter 6: The Many Worlds Alternative. What if the measurement problem in quantum mechanics isn't actually a problem at all? What if every possible outcome of every quantum measurement really does happen, just not in the same reality? This radical idea, known as the many worlds interpretation, suggests that there's no such thing as wave function collapse, because wave functions never collapse. Instead, reality constantly splits into parallel branches, creating infinite copies of the universe where every quantum possibility plays out simultaneously. The many worlds interpretation emerged in 1957 from the doctoral thesis of a young Princeton graduate student named Hugh Everett III. Everett was troubled by the conventional approach to quantum mechanics, which seemed to require two completely different types of physical processes. On one hand, quantum systems evolved smoothly and deterministically, according to the Schrödinger equation. On the other hand, measurements supposedly caused sudden, random collapse events that violated the normal rules of quantum evolution. Everett asked a simple but profound question. What if we take the Schrödinger equation seriously and apply it to everything, including measuring devices and observers? What if the universe always follows the mathematical rules of quantum mechanics, without any special exceptions for measurements or collapse events? When he worked through the mathematics, Everett discovered something extraordinary. The universal wave function doesn't need to collapse to explain why we observe definite measurement results. Instead, it splits into separate branches that each contain different versions of reality. To understand how this works, imagine a quantum measurement from the perspective of the universal wave function that describes everything in the universe, including the quantum system being measured, the measuring device, and the observer recording the result. Before the measurement, the quantum system exists in superposition, simultaneously in all possible states. The measuring device is ready to detect any of these possibilities. The observer is prepared to record whatever result the measurement produces. Now, according to standard quantum mechanics, the act of measurement should cause the quantum system to collapse into one definite state, triggering the measuring device to display a specific result and causing the observer to record that particular outcome. But Everett realized that if you apply the Schrödinger equation to the entire situation, including the measuring device and observer, something very different happens. Instead of collapse, the universal wave function evolves into a superposition of different measurement outcomes. In one branch of this superposition, the quantum system is in state A, the measuring device displays result A, and the observer records outcome A. In another branch, the quantum system is in state B. The measuring device shows result B, and the observer documents result B. All possible measurement outcomes occur simultaneously, each in its own branch of the universal wave function. The key insight is that observers can only experience one branch at a time, because they're part of the quantum system being described. You can't observe superposition from the inside because your own wave function has split along with everything else. From your perspective within any particular branch, it appears that one specific outcome occurred and all other possibilities vanished. But according to many worlds, those other possibilities didn't disappear. They continued evolving in parallel branches that you can no longer access or observe. This picture eliminates the measurement problem entirely. There's no need to explain when or how wave functions collapse because collapse never happens. There's no need to define what counts as a measurement because all interactions are treated equally according to the Schrödinger equation. There's no need to invoke consciousness or special physical processes, because the same quantum rules apply everywhere and every time. The mathematics of many worlds is surprisingly straightforward. The Schrödinger equation naturally describes how quantum systems become entangled with their environments, including measuring devices and observers. This entanglement process is what creates the branching structure of parallel realities, without requiring any modifications to standard quantum mechanics. The theory doesn't add anything new to the mathematical formalism. It simply takes the existing equations seriously and applies them universally. But the conceptual implications are staggering. If many worlds is correct, then every quantum event in the history of the universe has created countless parallel realities. Every time a radioactive atom decides whether to decay, reality splits into one branch where it decays and another where it doesn't. Every time a photon encounters a beam splitter, the universe divides into branches corresponding to reflection and transmission. Every time you make a decision that involves quantum processes in your brain, new versions of you split off to explore different choices. The number of parallel worlds created by this constant branching is almost incomprehensibly large. Consider that every atom in your body contains electrons making quantum transitions billions of times per second. Each transition potentially splits reality into multiple branches. Multiply this by all the atoms in all the objects around you, then by all the quantum events happening everywhere in the observable universe, and you get a picture of reality branching into astronomical numbers of parallel worlds every fraction of a second. These parallel branches don't exist in separate spaces or dimensions. They're all part of the same universal wave function, evolving according to the same physical laws in the same mathematical space. The branches become isolated from each other through a process called quantum decoherence, which makes it practically impossible for information to flow between different branches of reality. Decoherence occurs when quantum systems become entangled with large, complex environments. Imagine flipping a quantum coin that can exist in superposition, showing both heads and tails simultaneously. If this coin is perfectly isolated from its surroundings, it can maintain superposition indefinitely. But the moment the coin interacts with air molecules, photons, or any other environmental influences, it becomes entangled with those external systems. This entanglement rapidly spreads the quantum information about the coin's state throughout the environment. Air molecules that bounced off the head side carry different information than those that interacted with the tail side. Photons reflected from different orientations of the coin become correlated with the corresponding quantum states. Within an incredibly short time, the entire local environment becomes a detailed record of which branch of the coin's superposition actually occurred. Once this environmental entanglement is established, the different branches of reality become effectively isolated from each other. The heads branch contains an environment that consistently records heads, while the tails branch contains an environment that consistently records tails. These two branches can no longer interfere with each other because doing so would require coordinating the quantum states of countless environmental particles, which is practically impossible. Decoherence explains why we experience definite outcomes rather than quantum superposition in everyday life. It's not that superposition disappears or that wave functions collapse. Instead, we become locked into specific branches of reality by our entanglement with the environment around us. We can't observe superposition because we're embedded within particular branches that have definite, consistent histories. This process happens incredibly quickly for macroscopic objects. A grain of sand becomes entangled with its environment and splits into separate branches within nanoseconds. A cat's quantum state decoheres almost instantly through interactions with air molecules, thermal radiation, and its own internal biological processes. Human observers decohere essentially instantaneously through countless quantum interactions with their surroundings. But decoherence alone doesn't solve all the puzzles of many worlds. One of the biggest challenges involves understanding what quantum probabilities mean in a theory where every possible outcome actually occurs. In standard quantum mechanics, probabilities tell us the likelihood of observing different measurement results. But if all results happen in parallel branches, what does it mean to say that one outcome is more probable than another? This puzzle, known as the probability problem, has generated decades of research and debate among physicists and philosophers. Various solutions have been proposed, ranging from mathematical arguments based on the structure of the universal wave function, to anthropic reasoning about which branches can contain conscious observers capable of calculating probabilities. One approach suggests that probabilities emerge from the way conscious observers are distributed across different branches. If quantum mechanics creates more copies of you in branches corresponding to high probability outcomes and fewer copies in low probability branches, then from any individual perspective, it would appear that high probability events occur more frequently than low probability ones. Another approach focuses on the decision theoretic foundations of probability. If you're making choices about how to bet on quantum measurement outcomes, rational decision-making requires that you act as if the born rule probabilities apply, even in a many-worlds context where all outcomes occur. This suggests that probabilities reflect optimal strategies for navigating uncertainty rather than fundamental features of physical reality. Despite these challenges, many worlds has attracted significant support from physicists and cosmologists because it provides a complete, mathematically consistent interpretation of quantum mechanics without requiring any modifications to the underlying theory. Unlike objective collapse models that add new physical processes or consciousness-based interpretations that invoke mysterious mental influences, many worlds simply takes the Schrödinger equation at face value and follows it wherever it leads. The interpretation also offers elegant solutions to various puzzles in quantum mechanics and cosmology. The measurement problem disappears because there are no special measurement processes. The origin of classical behavior is explained through decoherence rather than mysterious collapse mechanisms. Even the fine-tuning problems in cosmology might be addressed if our universe is just one branch among countless others with different physical constants and initial conditions. Many worlds also provides a natural framework for thinking about quantum computation and quantum information processing. Quantum computers appear to derive their power from exploring multiple computational paths simultaneously, which fits naturally with the many worlds picture of parallel processing across multiple branches of reality. The quantum speedups observed in certain algorithms might reflect the universe's ability to perform calculations in parallel across exponentially many branches. Recent developments in quantum technology have created new ways to test the implications of many worlds. Experiments with quantum computers and quantum communication systems are probing the boundaries between quantum and classical behavior with unprecedented precision. While these experiments can't directly prove or disprove the existence of parallel worlds, They can test the mathematical predictions that distinguish many worlds from alternative interpretations. The interpretation also raises fascinating questions about personal identity and the nature of consciousness. If reality constantly splits into parallel branches containing multiple copies of yourself, which version is the real you? Do all these copies have equally valid claims to being your continuation, or is there something special about the particular branch you happen to experience? Some philosophers argue that many worlds dissolves the traditional notion of personal identity entirely. Instead of being a single, continuous self moving through time, you might be better understood as a constantly branching tree of related conscious experiences, with each branch representing a slightly different version of your ongoing story. Others suggest that consciousness itself might play a role in determining which branches of reality we experience. Perhaps conscious observation doesn't cause a wave function collapse, but it does select which branch of an already existing superposition we find ourselves in. This could provide a way to maintain the special role of consciousness in quantum mechanics, while avoiding the problems of consciousness-induced collapse. The many worlds interpretation also connects to deep questions about the nature of mathematical reality. If the universal wave function contains all possible branches of reality, then perhaps everything that can exist mathematically does exist physically. This suggests a profound unity between mathematics and physics, where the distinction between abstract mathematical structures and concrete physical reality becomes meaningless. These connections have inspired speculative ideas about the ultimate nature of existence. Some researchers propose that our universe is essentially a massive quantum computation, with the branching structure of many worlds representing different computational paths being explored simultaneously. Others suggest that consciousness might be a fundamental feature of reality that emerges whenever information processing reaches sufficient complexity, regardless of which branch of the multiverse it occurs in. The experimental implications of many worlds remain largely indirect, since we can only observe one branch of reality at a time. However, the interpretation does make testable predictions about the emergence of classical behavior through decoherence, the persistence of quantum coherence in isolated systems, and the scaling properties of quantum entanglement in complex systems. As quantum technology continues advancing, we may develop increasingly sophisticated ways to probe the boundaries between quantum and classical physics. Experiments with larger and more complex quantum systems might reveal signatures of the branching process that creates parallel worlds. Quantum computers might eventually become powerful enough to simulate the decoherence dynamics that govern how reality splits into separate branches. The many worlds interpretation forces us to radically expand our conception of reality. Instead of a single universe evolving through time, we might inhabit an ever-expanding multiverse where every quantum possibility is explored in parallel. The reality we experience is just one thread in an infinite tapestry of parallel stories, all equally real, but separated from each other by the fundamental quantum processes that govern the evolution of information and consciousness. Whether or not parallel worlds actually exist, the many worlds interpretation has profoundly influenced how physicists think about quantum mechanics, reality, and our place in the cosmos. It demonstrates that taking the mathematics of quantum theory seriously leads to conclusions that challenge our most basic assumptions about the nature of existence itself. In doing so, it opens new avenues for understanding the deep connections between physics, mathematics, consciousness, and the ultimate structure of reality. Chapter 7: Laboratory Tests of Reality. Far beneath the Italian mountains, inside the Gran Sasso National Laboratory, scientists pursue one of humanity's strangest quests: to find direct evidence that reality itself makes choices. Shielded beneath the nearly 1 mile of stone to block cosmic radiation, researchers there are searching for traces of quantum wave functions collapsing on their own, spontaneous moments when the universe decides what actually exists. For almost a century, physicists have argued over whether wave function collapse is a genuine physical process or simply a mathematical trick to predict measurement outcomes. Now, with advanced detectors and ultra-quiet laboratories, it has become possible to test whether this collapse happens spontaneously, even when no one is watching. The key ideas come from objective collapse theories such as the GRW, CSL, and Diossi-Penrose models. These propose that every quantum system occasionally collapses into a definite state, not because of measurement or observation, but as part of nature's own behavior. In these theories, the universe does not wait for a conscious observer. It constantly and randomly localizes its possibilities into reality. If such spontaneous collapses occur, they should release tiny bursts of electromagnetic radiation, collapse photons, whose properties depend on the details of the theory. Detecting this radiation would confirm that collapse is a real, physical event. But the signals are unimaginably faint. Searching for them is like listening for a whisper during a thunderstorm. To detect these faint flashes, scientists use ultra-pure germanium crystals, cooled to only a few degrees above absolute zero. Germanium is an ideal semiconductor. It can sense individual photons, can be purified to remove radioactive contamination, and remain stable at extremely low temperatures. The detectors, often weighing several kilograms, are surrounded by thick layers of copper and led to block stray radiation. The entire apparatus is chilled to about minus 200 degrees Celsius, using liquid nitrogen and complex refrigeration systems. Yet even this extreme shielding cannot block all interference. Cosmic rays, high-energy particles from distant stars and supernovas constantly strike the Earth's surface, creating showers of secondary radiation that could mimic the sought-after signals. That is why laboratories like Gran Sasso are located deep underground, with almost 4,000 meters of water-equivalent rock above them, reducing cosmic interference by nearly a millionfold. Still, natural radioactivity in surrounding materials produces gamma rays and other background radiation. Every screw, wire, and crystal used in these experiments must be made from materials with minuscule traces of radioactive elements. Scientists go to extraordinary lengths to ensure their instruments are quieter than any others on Earth. The experimental procedure itself is simple in theory, but demanding in practice. The germanium detector is monitored for spontaneous photon emissions that cannot be traced to known sources. According to collapse theories, these random photons should appear occasionally, with energies in the X-ray range and no correlation to external events. The problem lies in distinguishing real collapse photons from the overwhelming background noise of natural radiation, thermal fluctuations, and electronic interference. Years of data must be collected, and every possible source of error modeled, before scientists can claim a result. One of the earliest and most influential efforts was the IGX collaboration, active during the late 1990s and early 2000s. Using an 8-kilogram germanium crystal, IGX primarily searched for neutrinoless double beta decay, a rare nuclear process, but their detectors were sensitive enough to test for spontaneous collapse radiation as well. After more than 500 days of observation, the team found no sign of the continuous X-ray emissions predicted by the CSL model. This null result placed strong limits on the strength and frequency of possible collapse events, forcing theorists to adjust their models. More recent experiments, such as those by the Cuore collaboration at Gran Sasso, have achieved even greater sensitivity. Cuore uses nearly 1,000 tellurium dioxide crystals cooled to only a few thousandths of a degree above absolute zero, about 20 millikelvin. This makes it one of the coldest known places in the universe. At such temperatures, atoms barely move, drastically reducing background noise. Cuore also employs transition edge sensors, which detect individual photons with remarkable precision. These devices rely on materials that are balanced between superconducting and normal states. The absorption of even a single photon slightly changes their resistance, producing a measurable signal. Combined with Cuore's ultra-low temperature and radiation shielding, This technology allows scientists to detect events of extraordinary faintness. The results from Cuori and similar laboratories have further constrained objective collapse theories. The absence of any detectable collapse radiation suggests that if spontaneous localization occurs, it must be far weaker or rarer than many models once proposed. Certain parameters in the CSL and Diossi-Penrose models are now ruled out, while others remain viable but elusive. However, null results do not prove that collapse theories are wrong, only that the predicted effects are smaller than we can currently detect. The search continues on multiple fronts, not only underground, but also in new types of quantum systems, where the boundary between quantum and classical worlds can be probed more directly. One promising line of research involves levitated nanoparticles, tiny objects suspended in vacuum by optical or magnetic fields. These particles can be isolated from their surroundings so well that they exhibit quantum behavior on surprisingly large scales. If spontaneous collapse is real, there should be a point where these particles can no longer maintain quantum superpositions, even in perfect isolation. By measuring how long these superpositions last and how they decay, scientists can test whether the breakdown follows known environmental patterns or hints at intrinsic collapse mechanisms. Another frontier explores biological systems. Evidence of quantum coherence in photosynthesis, bird navigation, and other life processes suggests that quantum effects can persist even in warm, noisy environments. Some researchers wonder whether objective collapse might help explain why quantum behavior is limited in living systems. Experiments are now probing whether large biomolecules can sustain superposition and whether their eventual collapse matches predictions of spontaneous localization. Advances in quantum technology have opened yet another testing ground. Quantum computers and communication systems routinely manipulate complex superpositions involving many particles. As these systems scale up, they approach the regimes where objective collapse theories predict coherence should fail. If quantum computers ever encounter an unexplained source of error that cannot be corrected, it could reveal the fingerprints of spontaneous collapse itself. In this sense, the race to build larger quantum processors doubles as an experiment in the foundations of physics. Beyond the Earth, space-based laboratories promise even purer conditions. Without atmospheric radiation and seismic noise, orbiting experiments can test whether gravitational fields influence collapse rates, as proposed in the Diossi-Penrose model. The European Space Agency and other organizations are planning missions to study quantum systems in microgravity, where environmental interference is minimal and collapse effects might finally emerge from the noise. A few researchers even revisit the old question of consciousness. Does awareness itself play any role in quantum measurement? Though most physicists reject this idea, some experimentalists propose clever ways to test whether observation by a conscious agent affects outcomes differently from mechanical measurement. Defining and isolating conscious observation in a rigorous way remains immensely difficult, but the fact that such ideas can now be approached experimentally shows how far the field has come. In the end, these tests are about more than collapse theories. They probe the very architecture of reality. They ask whether the universe's transition from possibility to actuality happens through physical events we can measure, or through interactions too subtle to detect. Even when results come back empty, each experiment tightens the theoretical boundaries, refines our understanding, and drives technology forward. As sensitivity improves, through colder temperatures, quieter detectors, and larger quantum systems, we move closer to answering a question first asked nearly a century ago. Is wavefunction collapse real? Whether the answer lies buried beneath mountains, suspended in vacuum, or orbiting above the Earth, the search itself deepens our grasp of the quantum world and our place within it. In listening for the faint murmur of reality deciding what to be, we continue one of science's most profound experiments, the attempt to catch the universe in the act of becoming real. Chapter 8: The Information Paradox. Information may be the true currency of the universe. Not matter or energy, but the pure data describing what has happened, what is happening, and what could happen next. From this perspective, quantum mechanics is not about collapsing wave functions or splitting worlds. It is about how information flows and spreads, creating the appearance of classical reality from quantum foundations. The information-based approach to quantum mechanics began with one key realization. When a quantum system becomes entangled with its environment, its information does not vanish. It is simply dispersed among countless surrounding particles. This process, known as quantum decoherence, may explain the emergence of classical behavior without altering the basic laws of quantum mechanics. Imagine information as water poured into a vast network of pipes. The water never disappears. It diffuses until it becomes impossible to recollect into a single glass. In the same way, when a system's quantum information spreads through its environment, it becomes so diluted that recovering the original state is practically impossible. This dispersion happens astonishingly fast. A single dust grain floating in air collides with millions of gas molecules every second. Each impact carries minute fragments of information about the grain's quantum state into the surrounding air. Within microseconds, that information has been scattered among astronomical numbers of particles. In theory, one could reverse all these interactions and recover the original state, but in practice, controlling trillions of particles with perfect precision is impossible. The information is preserved, yet forever inaccessible. This inaccessibility gives rise to what appears to be classical behavior. Once information about a quantum superposition leaks into the environment, interference between its branches becomes impossible. The system seems to collapse into a definite state, not because a physical change occurs, but because environmental information prevents interference that would reveal its quantum nature. Information theory, originally developed for communication and computation, turns out to describe this process precisely. One essential concept is quantum entanglement, which produces correlations between systems stronger than any classical relationship. When two particles become entangled, measuring one instantly provides information about the other, even across great distances. This does not violate relativity. The connection is established at the moment of entanglement. Entanglement also explains how quantum information escapes into the environment. As a system in superposition interacts with environmental particles, the whole ensemble becomes a shared, correlated state. Each environmental particle holds partial information about which branch of the superposition occurred. Erasing this information to restore interference would require reversing all those entanglements, an exponentially difficult task as the number of particles grows. This exponential difficulty explains why macroscopic objects behave classically. A single isolated quantum particle can maintain superposition indefinitely, but objects composed of trillions of particles interact continuously with their environments, producing an overwhelming flood of entanglement. The environmental information grows so fast that no process could possibly maintain coherence. Thus, the classical world emerges not because quantum rules fail, but because information flow exceeds any feasible control. Recent advances show that this emergence links deeply to thermodynamics. The second law, which states that entropy always increases, may reflect the same process. As quantum information spreads, it becomes inaccessible. The arrow of time itself might result from this irreversible loss of accessible information. Quantum information theory has revealed that measurement, thermodynamics, and even consciousness may all connect through information flow. In quantum error correction, for instance, information is protected from decoherence by distributing it redundantly across multiple systems. If some are disturbed, the information can still be recovered. Intriguingly, nature seems to perform its own kind of error correction. Environmental particles store overlapping copies of a system's state, creating a distributed memory that preserves classical information even as quantum coherence vanishes. This redundancy explains the stability of the classical world. When you observe an object, You're not reading information within it directly, you are sampling the countless environmental copies of that information. Even if some records are lost, many backups remain. Classical reality, in other words, is a consensus built from redundant environmental data. This idea reframes the measurement problem. Measurement need not involve a special collapse or conscious observer. Instead, it occurs when a device or observer accesses the environmental information network surrounding a quantum system. Measuring does not alter reality. It extracts data already encoded in the environment. The border between quantum and classical behavior, therefore, depends not on size or mass, but on information availability. Well-isolated systems with minimal environmental data remain quantum. Heavily entangled systems appear classical. Understanding these information flows has also reshaped our view of entanglement itself. It is not merely a mathematical abstraction, it forms genuine physical networks that distribute correlations through space and time. Some theorists propose that these entanglement networks are the fabric of space and time. In this vision, space-time geometry emerges from the pattern of informational connections among quantum systems. Space and time, then, are not fundamental. They are emergent properties of quantum information. This radical idea touches the deepest problems in physics, including the quest to unify quantum mechanics and general relativity. If space-time reflects information networks, then understanding information flow could unlock a theory of quantum gravity. It might even resolve the infamous black hole information paradox. Stephen Hawking's early calculations suggested that information falling into a black hole would vanish forever when the black hole evaporates, seemingly violating quantum laws. Yet, if information can be stored in entanglement correlations between a black hole and its environment, it may not be lost at all, only encoded in subtle patterns that re-emerge as the black hole evaporates. These insights extend beyond physics into questions of consciousness. If classical reality arises from distributed information processing, consciousness itself might represent a special form of information integration within biological systems. This does not imply that consciousness causes quantum collapse. Rather, it suggests that brains are advanced information processors that interpret and organize the environmental data defining classical reality. Neuroscience supports this view. The brain operates through vast networks that share and integrate information across multiple regions, networks strikingly similar to the information webs that produce classical behavior in quantum systems. Some researchers even speculate that consciousness involves quantum-level information processes that classical computers cannot emulate. Though highly speculative, such ideas illustrate how quantum information theory is reshaping how we think about the mind. Quantum computing has given scientists powerful tools to test these ideas experimentally. By precisely controlling quantum information, researchers can observe how it spreads, entangles, and decoheres, revealing mechanisms once purely theoretical. These studies also demonstrate how fragile quantum information is and why maintaining coherence at scale is so difficult. Protecting quantum data requires continuous error correction, actively countering the natural information leakage into the environment. These challenges mirror the same limits that govern why everyday objects behave classically. As quantum computers grow larger, they face exponentially increasing demands for information control. This mirrors the universal principle that defines the quantum classical divide. The more particles and interactions involved, the more impossible perfect information recovery becomes. Looking forward, quantum information theory promises to reshape fundamental science. It links physics, thermodynamics, computation, and even cosmology under a single principle. That information is the most basic element of reality. Matter, energy, and space-time may all emerge from patterns of information flow. The measurement problem, long considered one of physics' greatest mysteries, may ultimately prove to be a question not of physical change, but of information accessibility. When we observe something, we are merely gaining access to specific information channels within the universe's vast informational web. The universe may not choose between quantum and classical behavior. It may simply reveal different aspects of one underlying information-based reality. In the end, the information revolution in physics invites us to reimagine the universe as a vast computation, an ever-evolving network of entanglement, correlation, and redundancy. Reality itself might best be understood not as a collection of particles moving through space and time, but as patterns of information continuously flowing and transforming, giving rise to the world we experience. Chapter 9: Consciousness and the Quantum Mind. For most of modern science, the idea that quantum mechanics could play a role in biology seemed impossible. The warm, watery, and chaotic environment inside living cells was thought to destroy fragile quantum effects, such as superposition and entanglement, almost instantly. Yet discoveries over the past few decades have overturned that assumption. Nature, it turns out, has found remarkable ways to use quantum mechanics to enhance life's efficiency. And this has revived an even deeper question. Could consciousness itself arise from quantum processes? The biological quantum revolution began with one of life's most familiar miracles: photosynthesis. Every green plant converts sunlight into chemical energy with astonishing precision, far surpassing any solar technology humans have created. For more than a century, scientists assumed this process followed classical physics. But in the early 2000s, researchers uncovered something extraordinary. When a photon of light strikes a photosynthetic complex, its energy does not simply bounce randomly until it reaches the reaction center. Instead, it simultaneously explores many possible routes in a state of quantum superposition, selecting the most efficient path almost instantly. This quantum coherence, lasting for hundreds of femtoseconds, enables energy transfer with near-perfect efficiency. Imagine navigating a maze while being able to try every path at once and immediately choosing the shortest one. That is what nature achieves through quantum mechanics. Even more astonishing, this coherence persists in warm, wet cellular conditions that classical physics says should destroy it. The secret lies in a phenomenon called environmentally assisted quantum transport, where molecular vibrations and noise do not ruin the quantum state, but help guide energy along optimal routes. This discovery opened scientists' eyes to the hidden quantum world within biology. Quantum tunneling helps enzymes catalyze reactions. Birds navigate Earth's magnetic field using quantum entanglement in their eyes. And the human sense of smell may depend on molecules vibrating at distinct quantum frequencies. Quantum effects, once thought too delicate for biology, appear woven into life itself. These insights naturally led researchers to the brain, the most complex biological system known. If plants and bacteria can harness quantum mechanics, might the brain do so as well? Some scientists believe that consciousness itself may depend on quantum information processing beyond the reach of classical computation. Among the boldest of these proposals is the orchestrated objective reduction theory by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that quantum computations occur inside microtubules, microscopic protein filaments that structure neurons. In this view, microtubules sustain quantum superpositions that allow the brain to integrate vast amounts of information and generate unified conscious experience. According to the theory, when these quantum states reach a certain threshold, they collapse through a gravitational process called objective reduction, producing discrete moments of awareness, roughly 40 times per second. Consciousness, then, would arise from rhythmic quantum events within the brain's cellular architecture. Critics long argued that the brain is far too warm and noisy for such coherence to survive. Random molecular interactions should cause quantum states in microtubules to decohere within trillionths of a second. But the discoveries in photosynthesis and other biological systems have softened this objection. If plants can maintain coherence in similar environments, perhaps evolution has also equipped the brain with comparable mechanisms to protect and exploit quantum effects. Other models propose that consciousness may not require perfectly stable superpositions. Instead, it could emerge from more robust forms of quantum entanglement, linking different regions of the brain. Entanglement allows distant particles, or perhaps neurons, to share information instantaneously, potentially explaining how the mind unites sensory data into a single, seamless experience. Some researchers point to quantum tunneling in ion channels, the gateways that regulate electrical signaling in neurons. The precise timing of neural firing might rely on quantum effects that amplify sensitivity and coordination, subtly shaping the neural patterns associated with awareness. The quantum mind hypothesis also intersects with the long-standing measurement problem in quantum physics. If consciousness involves quantum processes, perhaps observation by a conscious mind truly differs from inanimate measurement. This does not necessarily mean consciousness collapses wave functions, but conscious systems might uniquely access quantum information and translate it into classical perception. In this view, consciousness could represent an advanced form of quantum information integration, a biological mechanism for bridging the quantum and classical worlds. The brain may function as a quantum classical interface, interpreting decohering quantum data into the stable experiences we call awareness. Testing these ideas is extraordinarily difficult. Quantum effects occur on timescales and spatial dimensions far smaller than conventional neuroscience can observe. Evidence for quantum biology often comes indirectly, from the remarkable efficiency or sensitivity of living systems, rather than from direct observation of entanglement or superposition. Still, new experimental tools are closing the gap. Ultrafast laser spectroscopy has already captured real-time quantum coherence in photosynthetic complexes. Similar approaches might one day detect comparable effects in neural tissue. Quantum sensors capable of measuring faint magnetic or electric fields with unprecedented precision may reveal entanglement or coherence within the brain's microscopic structures. Neuroimaging methods such as functional magnetic resonance imaging and electroencephalography might also detect indirect traces of quantum information processing. Even anesthesia research offers clues. If consciousness depends on quantum coherence, anesthetics could work by disrupting those states, explaining how they switch awareness off and on. Beyond neuroscience, quantum biology promises revolutionary technologies. If living systems can maintain quantum coherence under everyday conditions, engineers might design quantum computers or sensors that operate at room temperature. Quantum-inspired medical devices, drug design, or diagnostic tools could harness nature's mastery of the quantum world. The implications extend to philosophy as well. If consciousness depends on quantum effects, then mind and matter intertwined at the most fundamental level. Some philosophers see this as a potential bridge between science and subjective experience, even offering a natural framework for understanding creativity, intuition, or free will. If human choices emerge from quantum indeterminacy within the brain, perhaps not every decision is predetermined by prior physical states. Others caution that randomness is not freedom. Quantum uncertainty alone does not create agency. True free will may require principles beyond both classical determinism and quantum chance. The quantum mind hypothesis, while suggestive, does not yet solve the mystery of why physical processes, quantum or otherwise, give rise to inner experience. Nonetheless, the discovery that biological systems routinely exploit quantum mechanics has transformed our understanding of life. The brain, as nature's most sophisticated creation, likely uses physics at every available scale, from molecular chemistry to quantum dynamics, to achieve its extraordinary abilities. Whether or not quantum mechanics directly produces consciousness, exploring these possibilities deepens our insight into both biology and physics. It reminds us that the boundary between the quantum and classical worlds is not a hard wall, but a living continuum. The quest to understand consciousness may ultimately reveal not just how the brain works, but how reality itself unfolds from the quantum fabric beneath. The age of quantum biology has shown that life and the quantum realm are far more connected than anyone once imagined. Perhaps consciousness is the ultimate expression of that connection, or perhaps it is simply another manifestation of the same deep unity that links light, matter, and life. Whatever the truth proves to be, the study of the quantum mind challenges us to look beyond the limits of classical thought and glimpse a universe where awareness and reality may be two sides of the same wave.